We will now begin our final topic, the Laplace transform, and using it to solve differential equations. So all of the methods we have studied so far, when looking at a non-homogeneous linear equation, the driving force, that f of t, had to be continuous. We are now going to study a tool that would allow us to solve such an equation where the driving force is discontinuous. So we let f be a function that is defined for t greater than or equal to 0. Then this integral, which we represent L f of t, which is the integral from 0 to infinity of e to the negative s times t times f of t dt, is the Laplace transform of f, provided the integral exists. Or I should say, converges. This is named in honor of the French mathematician and astronomer Pierre-Simon Marquis de Laplace. We will now calculate some Laplace transforms. So let's look at the Laplace transform of 1. So by definition, this is the integral from 0 to infinity of e to the negative st times 1 dt, which is just the integral from 0 to infinity of e to the negative st dt, which is negative 1 over s e to the negative st evaluated for t equals 0 to infinity. So we get negative 1 over s times e to the minus infinity minus e to the 0. Now this is understood to be a limit. That converges to 0. So we're left with one over s. Let's now look at the Laplace transform of t. So it's the integral from 0 to infinity of e to the negative st all times t dt. So the integral from 0 to infinity, t e to the negative st. This is going to require integration by parts. So we let u be t, which means that du is simply dt. dv will be e to the negative st dt, and so v, negative 1 over s e to the minus st. So our Laplace transform is negative t over s e to the negative st evaluated t equals 0 to infinity minus the integral from 0 to infinity of negative 1 over s e to the negative st dt. So we're going to have negative t over s e to the negative st evaluated from 0 to infinity plus 1 over s times the integral from 0 to infinity of e to the negative st dt. So negative t over s e to the negative st minus 1 over s squared e to the negative st from 0 to infinity. So this will go to minus 1. So this whole term will wind up converging to 1 over s squared, negative 1 over s squared. We now just have to look at this first term. So we'll get negative limit as t goes to infinity of t over s e to the negative st plus 0. This limit is 0, which means this whole term will go to 0. And we're left with minus negative 1 over s squared, which is just 1 over s squared. So the Laplace transform of t is 1 over s squared. Let's look at now the Laplace transform of e to the 5t. So we'll have the integral from 0 to infinity, e to the negative st times e to the 5t dt. So it's 0 to infinity, e to the 5 minus s all times t dt. So it's 1 over 5 minus s e to the 5 minus s t, evaluate from t equals 0 to infinity. So 1 over 5 minus s times the limit as t goes to infinity of e to the 5 minus s times infinity, times t, minus e to the 0. To find this limit, we can rewrite it as negative s minus 5 times t minus e to the 0. That goes to 0, and so we're left with negative 1 over 5 minus s, which is 1 over s minus 5. An interesting property about the Laplace transforms is that they are linear. That is, for functions f and g, Laplace transform of alpha f of t plus beta g of t is equal to alpha times the Laplace transform of f of t plus beta times the Laplace transform of g of t for any alpha beta, which are real numbers. They actually don't have to be real numbers. They can be complex numbers, as long as they're constants. Now, this follows from the fact that the Laplace transform is an integral, and the integral is linear. So I'm now going to give you the Laplace transforms of several basic functions. So the first one, we already saw. The Laplace transform of 1 is just 1 over s. The Laplace transform of t to the n for any integer n is n factorial over s to the n plus 1 for any positive integer n. The Laplace transform of e to the at is 1 over s minus a. Laplace transform of sine of kt is k over s squared plus k squared. The Laplace transform of cosine of kt is s over s squared plus k squared. Laplace transform of the hyperbolic sine of kt is k over s squared minus k squared. And the Laplace transform of the hyperbolic cosine of kt is s over s squared minus k squared. So a function f is said to be of exponential order if there exists constants c, m which is greater than 0, and t which is greater than 0, such that the absolute value of f of t is less than or equal to big M e to the ct for all little t greater than big T. We can now look at the existence theorem, which states if f is piecewise continuous on 0 to infinity and of exponential order, then the Laplace transform of f of t exists for s larger than c. All right, so we're going to prove this. Notice that we're going to have the Laplace transform f of t can be written as the integral from 0 to capital T of e to the negative st f of t dt plus the integral from big T to infinity of e to the negative st f of t dt. And we're going to write this as I1 plus I2. So this integral will be represented by I1. This integral will be represented by I2. Now, I1 must exist because it can be written as a sum of integrals over intervals on which the integrand, e to the negative st f of t, is continuous. Now, we have to look at I2. So now we have to show that I2 converges. Well, f is of exponential order. Which implies that there exists constants c, big M larger than 0, big T larger than 0, such that the absolute value of f of t is less than or equal to big M e to the c big T for all t larger than t. That is by the definition of exponential order. Therefore, we can write the absolute value of I2 is less than or equal to the integral from big T to infinity of the absolute value e to the minus st f of t dt, which is now less than or equal to big M times the integral from big T to infinity of e to the minus st e to the c big T, I'm sorry, little t dt. So this here should be a little t. Did I mess up the definition? I may have. I did. This is supposed to be c little t. Sorry about that. This integral evaluates out to big M e to the negative quantity s minus c times big T all over s minus c. And of course, this has to be true for little s larger than c. Well, that means that this converges. Therefore, I2, the absolute value of I2, converges by a comparison test, by integral comparison, which you should have learned in Calculus 2. Which implies that I2 converges for s larger than c. Therefore, we can conclude that the Laplace transform of f of t exists for s larger than c, which is what we were after. So that concludes this lesson. I hope you've learned something, and we will see you in the next one.